All right, this is a CHEM 1412 final exam review part 1. So in this part, I'm going to talk about intermolecular forces, kinetics, so basically the first 3 chapters of the semester. All right, so the exam is about 70 questions. It is 70 questions, not about. It's 70 questions total. You'll have 110 minutes to take it. You're given some of the needed equations and all of the necessary constants. Now, one thing that I can tell you is don't waste your time on a problem where you can't get the answer. If you think you know how to solve it and you've put it in your calculator and you've written out how to do it and you're not getting one of the answers, don't sit there and play with the numbers for a long period of time because there's probably more answers that you will get and you're wasting time on a question that you're not sure about. So mark those as something you can go back to if you have enough time. If there's a question that you have no idea how to answer, skip it. Don't play with the numbers or play with the answers until you think you've found something. Save those for later as well. Okay, so this is from the current textbook, chapter 10. There's about 9 questions from it. Chapter 11, about 4, and chapter 12, about 10. So if you're worried about time to study, I would focus on chapter 10 and chapter 12 before going to chapter 11. All right, so here are some intermolecular forces vocabulary. You need to be very familiar with these terms so that you can answer questions properly. If you don't know what a word means that's in a question, you can't answer it correctly. So make sure that you know all this vocabulary. So you can pause the video if there's something that you don't know and write it down. Make sure that you've put it on a flashcard or something so that you can quiz yourself and make sure you know what it means. All right, so the first thing we come to is a dipole-dipole interaction. It's an electronegative. It's when an electronegative element pulls electron density away from a less electronegative element. So something weird has happened here on my slide, but I'm going to draw it down here. So if I have hydrochloric acid, let me make that. Okay, so it's a chlorine. It's bonded to a hydrogen. Now, if you know the periodic table and you know the trends from the periodic table, so if this is the periodic table, then moving to the right and up, excluding the noble gases, then you know that fluorine is the most electronegative, and right under fluorine is chlorine. So chlorine is pretty electronegative. It's going to be pulling the electron density that's in this bond towards itself. And so remember that a hydrogen atom only has 1 proton and 1 electron. So that 1 electron is in this bond. And if chlorine is pulling it away, then you really just have out here, you have this bald proton that becomes very positive. And chlorine, because it has a full valence shell, remember it should only have 7 valence electrons, it has a full valence shell and it's pulling these electrons towards itself, it's going to have a strong negative charge, so that if another hydrochloric acid gets close to it and the same thing is happening to it, then there's going to be a very strong attraction between this negative and this positive. So it's not a complete charge, it's a partial charge, but it's enough to where there's an attraction between these 2 separate molecules. And so that's a dipole-dipole interaction. So this is called when it's polar and it has, when it's polar like this, and this has a partial negative on one end and a partial positive on another end, that's called a dipole. Let me find a different color. Here we go. And since this also has a dipole, it's a dipole-dipole interaction. All right, the next one is an ion-dipole interaction. And so if we look at water, right, oxygen, hydrogen, hydrogen, and these lone pairs up here. And so remember, water is bent. Okay, it has this bent-looking structure on it. And oxygen's more electronegative than hydrogen, so there's a dipole here that is taking place. And when you put salt, okay, an ionic compound, into water, it's going to dissolve. We know that salt dissolves especially. So if I put NaCl in water, it's going to dissolve into sodium ions and chloride ions. And I just want to show for a second kind of how that happens so that you can remember what this process looks like. Okay, so this is sodium chloride in this picture right here. And so sodium chloride, because it's ionic, this is really an empirical formula, which means that the formula is reduced. So you have one sodium to every chloride. So when you put this in water, the water molecules, because of their partial charge here, right, the partial positive and partial negative charges, because of the dipole in it, they attack the ions. So remember, the chloride ions, let's see where my thingy is. The chloride ions right here, okay, the bigger green ones, because they have an extra electron, so they're going to be bigger, are attacked by the positive end, so the hydrogens, right? And then the blue ones, the sodium ions, the smaller ones, are attacked by the oxygen ends, the negative ends. And then they can be pulled off. And when they're pulled off, the water molecules surround the ions. It's what happens when a hydrolysis takes place, right? And so they surround the ion and they dissolve it. And that's what happens. And so each one of these ions in here will be dissolved by the water molecules until the saturation point is found, until no more salt can be dissolved. And so this right here is an ion-dipole interaction because the ion is attracted to the dipole, the polar nature of the molecule that is being attracted to. All right, hydrogen bonding. Hydrogen bonding is very, 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 very important. It's a dipole-dipole interaction, but it's more specific. So with water has a dipole. We saw that on the ion-dipole interaction on the slide before. But in this particular one, because oxygen is way more electronegative than many other atoms, and it's also very small, okay? When it's attached to a hydrogen, it pulls very hard. And so the electrons in this bond are being pulled way far up here. And so that makes hydrogen highly partially positive, and oxygen is very negative. And so it's going to have a stronger interaction with a neighboring dipole. But specifically, the hydrogen has to be attached to a nitrogen, oxygen, or fluorine. It can't be attached to chlorine or sulfur or something like that. It has to be attached to one of these three because they're very, very small and they're very electronegative. And so it causes a much stronger thing to occur than just a dipole-dipole interaction. Now, one thing do not get confused about, it is not a bond. It's called hydrogen bonding. I wish they called it hydrogen forces or something like that, but they don't. They call it hydrogen bonding. The force that happens here, okay, so this is just a force. It's not a bond, it's just a force. Okay, so it's not as strong as a covalent bond. It's definitely not as strong as an ionic bond, but it is something that that is very important in especially biochemical processes and biochemical molecules, and proteins and DNA and all that stuff. So this, if you remember in biology, in DNA, C always goes to G and A always goes to T, and that's because their hydrogen bonding can set up right. So in DNA, when you have G on one side and you have C on the other side and they go together, it's because their hydrogen bonds can line up. If this didn't occur and if this was an actual bond, then we couldn't replicate DNA without breaking bonds. And if we broke bonds, we'd end up breaking all of these bonds, and so it would just fall apart. But because this force is so strong, it can hold our DNA together, but we can also easily break it apart so that we can replicate. So make sure that when you know about hydrogen bonding, or when you think about hydrogen bonding, you think first water, and then you also think that it has to have nitrogen, oxygen, or fluorine attached directly to a hydrogen. Okay, it has to be attached directly to a hydrogen, so it can't be sitting somewhere else. So if we look right here at this is nitrogen attached directly to a hydrogen, all right? And so it's attracted to this oxygen here because they've got those lone pairs on there. This is hydrogen attached directly to a nitrogen. This is nitrogen attached directly to a hydrogen. Same over here, nitrogen directly to a hydrogen and nitrogen directly to a hydrogen, and they're attracted to another electronegative element that has a lone pair of electrons on it. So this hydrogen, because it's so positive and it's very electron deficient, it wants more electrons, it will be attracted to those lone pairs that are on the other electronegative elements. All right, London dispersion forces. So this is one of the forces that I always had problems visualizing because I thought that it was kind of intuitive that this could happen, but that it could be such a strong force was kind of confusing to me, but it is. So, but it's caused by an unequal distribution of electrons that initiates a partial positive charge on one side and a partial negative charge on the other side of a molecule. So if we have a molecule like and I'm just going to draw a small hydrocarbon chain. All right, so this is propane. If we have a propane molecule, then you could imagine that all these electrons that are involved in all of these bonds that are happening in here, right? If they all of a sudden were shifted to one side of the molecule, then that means this side would be partially negative, and then up here would be partially positive. And that's exactly what happens. So the bigger the molecule gets, the more this force can take place. And I'm just going to call them LDFs. Okay, so if you're just comparing molecules that have London dispersion forces, you just look for the molecule that has the biggest mass. So the forces that we've talked about are ion dipole, dipole dipole, hydrogen bonding, and London dispersion forces. So if they're talking about boiling points, then they want to know which one has the highest force. If they're talking about melting points, vapor pressure, any kind of physical property on a substance that or a solution, they want to know, they're asking about intermolecular forces. Which compound has the highest intermolecular force? And so I'm going to come down here and I'm going to tell you that hydrogen bonding is the strongest intermolecular force. Dipole dipole is next. And London dispersion is last. Now, ion dipole, that's a little different because this can take place, these three things can take place on just a molecule by itself because there's going to be more than one molecule in that sample, and so they can be attracted to themselves. Ion dipole requires an ion to be dissolved in a solvent, whereas these don't necessarily have to have that. So it's ion dipole is very easy to identify compared to these three things. So like I was saying, these up here, this is strongest to least strongest. Weakest, I guess. Weakest. All right. So up here where it's the strongest, they're going to have the higher boiling points because it's going to be harder to turn them into a gas, higher melting points, lower vapor pressure. Because they're going to have a hard time turning into a gas, so you have to put more energy into it. They're going to have a hard time turning into a liquid because they want to be close to one another. When they have these intermolecular forces, they want to stay close. And whenever you turn something into a gas, you have to spread it far apart, and so you have to overcome those interactions in order to get it to turn into a gas. So if it says which one of the following would have the highest boiling point, or which one of the following would have the highest melting point, you should pick the one that has the strongest intermolecular force. All right, so let's look at some questions here. Results of intermolecular forces. What intermolecular force is the reason for chlorine being a gas, bromine being a liquid, and iodine being a solid at room temperature? So these three things are all halogens, right? They're all in group 7 on the periodic table. But if you look, chlorine is a gas, bromine is a liquid, and iodine is a solid. And so the reason for that is because chlorine, Cl2, has a mass of 70. Bromine has a mass of 160, somewhere around there. And iodine has a mass of 152, I think, somewhere close to that, times 2. Oh, I'm sorry, that's not right. It's 252. 252. It's 126. So this is going to be London dispersion, because if chlorine is bonded to chlorine, well, it can't have a dipole because they're both of equal strength, right? This chlorine can't pull these electrons any closer to itself. This chlorine can't pull these electrons any closer to itself. So this is going to have the intermolecular force of just LDFs. And bromine's in the same boat, as well as iodine. So they all have LDFs, only this one has the biggest mass. So its London dispersion forces will be bigger. Okay. Which compound would be the most soluble in water? So in this one, what we're looking for is something that's going to have a dipole interaction with water, because like dissolves like. Right? So polar will dissolve polar, while nonpolar things dissolve nonpolar things. So when I look at this molecule right here, the first thing I notice is this big, huge, it's called a hydrocarbon chain, because it's just hydrogen and carbon. And so that big, huge chain is nonpolar. They're always nonpolar. Okay, so if it's nonpolar, it's not going to dissolve in water very well. And so the longer this chain is, the more this molecule becomes nonpolar. Even though this end right here might be slightly polar, when these get longer and longer, it's not going to want to dissolve in water. So this one down here at the very end has the shortest chain with chlorine, and so this molecule, which is going to look like this, is going to, this bond right here is going to be very polar. And so it's going to be slightly positive over here and slightly negative, whoops, slightly negative on that end, which will cause an interaction with water. And the hydrogen end of water, H2O, right, will be attracted to the negative end of chloromethane. All right. Why does CH3 boil at almost 230 degrees higher than CH4? So CH3OH, methanol, looks like this, while methane looks like that. And so, let's see if I can move this. Nope, it's all stuck together. All right. Methane is nonpolar. There is nothing here. Remember, hydrocarbon, hydrogen and carbon bonded together are not going to be polar at all. So this is nonpolar. So it doesn't have a dipole-dipole. It can't have hydrogen bonding. There's no oxygen, fluorine, or nitrogen in there. So that means that this only has London dispersion. While in this molecule right here, because this oxygen is bonded directly to hydrogen, that is going to have hydrogen bonding. So because of that, right, remember hydrogen bonding is the strongest intermolecular force of the three that we're comparing. So this is definitely going to have a higher boiling point because it has hydrogen bonding in it, whereas this one, oops, this one, it does not. All right, vapor pressure and boiling point. So I put this on here because a lot of students don't understand what vapor pressure is. It's kind of hard to understand, so I'm going to try to explain this with a phenomenon that we're all kind of familiar with. In the summertime here in Texas, I have a tendency to leave lots of water bottles that are half full in my car. And if you've ever done that before, and you've gotten in your car and then you've turned your AC on high blast, and it, like on the passenger side, if it's going to the floorboard as well, it's pointed directly at those water bottles, then the water bottles start to crinkle and crack. And that's because the temperature inside of the water bottle is coming down, right? And they have the gas inside of the water bottle. So let me draw a water bottle here as best that I can. Okay, if it's half filled, right, and this is H2O here floating around, as the temperature goes up outside and then in the car, right, and inside the car it might get up to 180 degrees or whatever, some of these water molecules that are sitting at the very top of this can come up into the gas phase. As the temperature goes up, more water molecules can come up into the gas phase. And so as it gets hotter and hotter in the car, we get more of these molecules going into the gas phase. Well, eventually this water bottle has to bulge out. Usually the bottom bulges out first because it doesn't have enough room for all the gas molecules that are building up inside of the bottle, right? And then once we cool it down, the molecules go back down. And now, of course, we know that water is going to turn into a gas at 100 degrees Celsius or 212 degrees Fahrenheit. Now, it's not going to get up to 212 degrees Fahrenheit inside of my car, so all of this water is not going to start boiling. But it's definitely, we can tell that there's something that's happened because the bottle is all bent out of shape. And so it's what the vapor pressure is going up inside of the container. And eventually, if we were to boil this water, the vapor pressure becomes, equal to the atmospheric pressure. So the pressure that we feel by all of the air on top of us and gravity pushing down on us. So that's the atmospheric pressure. So once the vapor pressure is equal to the atmospheric pressure, then all of the water molecules can turn into the gas phase, and that's the boiling point. So as the temperature goes up, the vapor pressure is going to increase until it reaches atmospheric pressure, and at that point, all of this is going to have the ability to turn into a gas. So let's talk about if the molecule has a high molar mass. So if the molecule has a high molar mass, then it's going to be harder to get it into the gas phase because they're going to be more attracted to one another. They're going to have, every molecule has London dispersion forces, even if it has dipole and hydrogen bonding. But if it has London dispersion forces, then they're going to be attracted to one another, right? So I'm just going to draw some random hydrocarbon down here. Oops. So let's see, 1, 2, 3, 4, 5, 6. So that's hexane. Hexane doesn't have that high of a boiling point, but it's much higher than, let's say, a hydrocarbon with only 2 carbon atoms and 6, like ethane, 2 carbon atoms and 6 hydrogen atoms. So if this has a partially negative on one end and a partially positive on another end, then they're going to be attracted to each other and they're going to want to be close to one another at those oppositely charged ends. And so it's going to be harder to get it to go in the vapor phase, meaning it's going to require higher boiling point to get there, and more of them will want to stay in the liquid phase, so it's going to have a much lower vapor pressure. So let me write that down here. The higher the intermolecular forces are, the lower the vapor pressure. Also, the higher the molar mass. The lower the vapor pressure. All right, so vapor pressure of a solution calculations. At 45 degrees Celsius, the vapor pressure of water is 71.93 millimeters of mercury. If 10 grams of urea is dissolved in 150 grams of water at 45 degrees Celsius, what is the vapor pressure of the solution? Okay, so this is one of those calculations where I don't believe they give you these formulas on the test, but you really don't need them, okay? So if you can understand what a percent is. All right, if we want to know what the pressure of the solution is going to be, we take the mole fraction of the solvent and multiply it by the original pressure of the solvent without anything in it. Okay, so if we look at, we're putting 10 grams of CH4N2O into 150 grams of H2O. And the reason that we would want to look at this in moles instead of in grams is because vapor pressure is directly related to the particles, not to the grams. And so just because something has more mass doesn't mean there's necessarily more particles of it. All right? And it says that the vapor pressure of pure water, so this by itself at 45 degrees Celsius is 71.93 millimeters of mercury. And we want to know what the vapor pressure is of this total solution. Okay? Mixed together. So the first thing I have to do is turn these masses into moles. So I've got 10 grams CH4 N2O, and the molar mass of CH4 N2O, I'm going to take the mass of carbon, which is 12, the mass of hydrogen is 1 times 4, the mass of nitrogen, 14 times 2, and the mass of oxygen, which is 16, and I'm going to add those all together. And I get that this equals 60 grams for every 1 mole. So there's 60 grams in 1 mole of that. So I'm going to divide by 60 grams, 10 divided by 60, so I get 0.167 moles of urea. And then I'm going to do the same thing for water. So I have 150 grams of H2O. There's 18 grams of water in 1 mole of water. So it's 150 divided by 18 is 8.33 moles of H2O. And so if I were to find the percent of water in this solution, then I would take the amount of water and divide by the total sum and then multiply by 100. But I don't want to find the percent, I just need the mole fraction. And so just like if you were to, in, I don't know, 2nd grade, find the fraction of students wearing blue shirts in your classroom, you would take the number of students wearing blue shirts divided by the total number of students in the class. So we're going to do the same thing here. We're just going to say the total moles is equal to 8.33 plus 0.167. And so that comes out to 8.497 moles. Okay, and rounded to sig figs, that would be 8.50. And we're going to take then to find the mole fraction of water. The fraction of water is 8.33 moles. And we're going to divide that by 8.50. And that gives us 16. Oops, I added it together. It gives us 0.98. So it's 98% water. All right, so I'm going to shrink this back down so that we can see the question again. Okay. And we want to know the vapor pressure of the solution. So that's the mole fraction. And the original pressure of the solution, I'm sorry, the original pressure of the water is 71.93. That's the vapor pressure of water at 45 degrees Celsius. So if it's 98% water, then that means that 98% of this should remain the same, while the rest is affected by the stuff that's dissolved in the water. So I'm going to take the pressure of the solution is going to be equal to 0.98, the mole fraction, the fraction that's water, times the original pressure of water by itself. So 0.98 times 71.93 is equal to 70.49. Or I guess that would be sig fig 70.5 millimeters of mercury, because this should really have a 0 at the end. So that's the answer. All right, so these type of calculations can be kind of tricky sometimes for students. One thing you need to make sure of is that you know the definitions of all the different concentrations that you can calculate. And so mass percent is going to be exactly what it describes. It's going to be the mass of something divided by the total mass times 100 to get the percent. And then remember that molarity is always moles of the solute divided by liters of the solution. And this is liters of the total. Okay, it's not liters of your solvent, it's liters of all of it. And so it says the density of a 16 mass percent solution of sulfuric acid in water is 1.1094 grams per milliliter at 25 degrees Celsius. What is the molarity of the solution? So we're looking for molarity. So I know I have to find, to get molarity, I have to find moles of sulfuric acid, because that's the solute, in liters of the solution. Okay, so I have to find both moles of the H2SO4 and I have to find liters of the total solution. And so another thing that I'm given here is I'm given the mass percent. Now 16 mass percent means that I have 16 grams of sulfuric acid in 100 grams of total solution. Okay, I don't have 16 grams of H2SO4 and 100 grams of water. I have it in 100 grams of total solution. So I see a connection here. And I also know that my density is 1.1094 grams per milliliter. So there's a way to go from grams to milliliters, or from milliliters to grams. Now I have grams, right? I have 100 grams of solution, and I know that from my density that there's 1.1094 grams of solution in every milliliter. Whoa, that's backwards. That's weird. In every milliliter. And what I need up here is liters, not milliliters. So there's 1,000 milliliters in 1 liter. So if I divide all that out, 100 divided by 1.1094 divided by 1,000, then I end up with 0.0901 liters. So this is my liters of total solution. So I found my denominator here. Now I just have to find the moles of H2SO4, and I've got 16 grams of H2SO4. And so I can use my molar mass, which is 98. So 16 divided by 98 is 0.163 moles. And so that is my numerator. So I'm just going to take my moles of H2SO4 and divide by my total liters. So that would be 0.163 moles of H2SO4 and divide it by 0.0901 liters. And I end up with 0.553 moles per liter. So that's my molarity. Okay, so this is a heat curves, and this is the heat curve for water, right? Right here on the heat curve where we start at point A, it's going to be a solid, and we're going to heat up the solid, so it's at negative, 25 degrees right here, and we're going to heat it up. So as long as it stays below 0, it's still going to be a solid, it's just going to be gaining heat. And so it gains heat until it gets to the melting point at 0 degrees Celsius. Now at 0 degrees Celsius, it can then start to melt, and the temperature is going to stay flat. Its temperature is not going to increase until all the ice has eventually turned to liquid. And then once it's turned to liquid, if we keep heating it and we keep adding heat to it, it's going to start heating up to liquid. So between the temperatures of 0 to 100, it will remain a liquid. It's just going to continue to gain heat and gain heat and gain heat until we get to 100 degrees. Now at 100 degrees Celsius, it's going to start to boil. And it's going to boil and stay at 100 degrees until all of the water turns into steam or vapor or gas. And then once we have a gas, we can continue heating it. And so between above 100 degrees Celsius, it's going to be gas. It's just going to get hotter and hotter. All right, so from A to B, we're heating the solid, and we have a specific heat value of 2.09 joules per gram degree Celsius. And what that means is it means that it's going to take 2.09 joules for 1 gram to heat up 1 degree Celsius. So every single degree Celsius that we increase the temperature here of the ice, if it's 1 gram of that substance, it's going to take 2.09 joules. Now the temperature is changing here, right? Because this is temperature over here, and it's going up. And so that's why we have a degree Celsius here. While it melts from B to C, it's not going to change temperature. It's going to stay the same. And so for that, we have kilojoules per mole. All right? And then again, when we heat the water, it's joules per gram degree Celsius because the temperature, again, is rising. So it takes 4.18 joules for every gram of water that we heat up 1 degree Celsius. And then the vaporization, the phase change, of course, is not going to have a change in temperature, so it's just kilojoules per mole. And then when we heat a gas, it takes 2.01 joules per gram degree Celsius. Again, the temperature is changing. And so the first question here is, why is the delta H of vaporization so much larger than the delta H of fusion? Well, the delta H of fusion is melting the ice, right? So if we have ice, the molecules are really close together. Okay? And so we only have to separate them a little bit to turn them into a liquid. Now, if we want to turn it into a gas, we have to spread these molecules out way far apart, and so that it has to overcome all intermolecular forces. And that's why the delta H of fusion is always going to be so much larger than the delta H of vaporization, I'm sorry. The delta H of vaporization is always going to be so much larger, right? This is much longer than this is because we have to overcome those intermolecular forces. So if it has hydrogen bonding, it will have an even bigger delta H of vaporization than something that only has London dispersion forces. Okay, what calculations would you need to perform to find the amount of heat in segment CD. So if we needed to find the amount of heat for this segment right here, we would only have to use this. So if we weren't changing the phase for anything, right, and we were just seeing how much heat would be needed to raise it from, let's say, 25 degrees to 75 degrees, then you just take the change in temperature from 75 to 25 and multiply by the mass that you have times the change in temperature, and you'd be able to calculate the amount of heat. All right, and then the last one, how much heat would you need to add to convert 50 grams of water? So we've got 50 grams of water at 30 degrees, and we want to convert it to steam at 100 degrees Celsius. So liquid to gas. So on my heat curve up here, I'm going to take this from 30 degrees, which is about right here, all the way over to here. So I have to use the specific heat of the water, and I also have to use the delta H of vaporization. All right, so I'm going to take first the specific heat of water, which is 4.18 joules per gram degree Celsius, and I know that I want joules. Okay, I want joules. So if I want joules, and I've got joules over gram degrees Celsius, and that means I have to get rid of grams, and I also have to get rid of degrees Celsius. So I'm going to have to multiply by grams, which is 50. And then I'm going to have to multiply by however many degrees that I change. And so this is going to last from 30 degrees all the way up to 100 degrees. And so that's a 70 degree change. So if I multiply by both of those times the specific heat, I'll end up with joules. And so it's 4.18 times 50 times 70, and I get 14,630 joules. All right, so this is the first calculation. And then for the second calculation, I am going to use 40.7 kilojoules per mole. So again, if I want joules, I'm going to have to get rid of this moles here. And I've got 50 grams, right? Let's see, where do I want to write that? Let me make this smaller. I've got 50 grams of water, and there's 18 grams per mole. And so that's 2.78 moles of H2O. So that means that it's going to take 113.1 kilojoules to turn that 50 grams of water into steam, to vaporize it. So now I have to add these together. Now they have to be in the same unit, and so I'm just going to convert this 14,630 into kilojoules, right? And so that is the same thing as 14.6 kilojoules. So I'm going to add 14.6 and 113.1. And that gives me 127.7 kilojoules. So that's how much heat it would take to take 50 grams of water at 30 degrees Celsius up to turning it all into steam at 100 degrees Celsius. Okay, phase diagrams. Solid to liquid is melting, or you can also call it fusion. Liquid to solid is freezing. Liquid to vapor, vaporization. Vapor to liquid, condensation. Some things that people forget: solid to vapor is sublimation, and vapor to solid is deposition. So this is a phase diagram. Here's the triple point. That's when something can be found as a solid, liquid, and gas at the same time. So it shows you the temperature and also the pressure. So pressure is over here on the y-axis, and temperature is down here on the x-axis. And here's your critical point. Past the critical point, you cannot tell the difference between a liquid or a gas anymore. Okay, so what phase changes would take place if you went from 1 to 2? So if you went directly from 1 to 2, that would be sublimation, because it would be going from a solid to a gas. Remember that these are always going to be solid, liquid, and gas, like that. All right? And so if you went from 2 to 3, then it would be condensation, because it would be going from a vapor to a liquid. All right? And if it was going from 3 to 1, right? Ooh, you can't really see that. If it was going from 3 to 1, then it would be freezing, because it would be going from a liquid to a solid. So as soon as it crosses this line that separates solid to liquid and liquid to solid, it changes phase. Okay, so pressure has a big, huge part in what the freezing point of something is. We call the normal freezing point and normal boiling point at 1 atm, because that's atmospheric pressure at sea level. So what we feel here. Now what you feel here and what you feel in Pikes Peak is something totally different. It has a lower pressure, and so its boiling point is going to be much lower, because it doesn't take as much to get the vapor pressure to equal the atmospheric pressure. All right, next. Okay, so in this equation, or with this equation, really what you need to know is you need to know how to look at these. If you see something like this, right, where this is going to be something that's not changing, the delta H of vaporization is going to be the same for a substance, as well as R. R is the gas constant. Okay, then you would have a line where the y-axis would be the natural log of P, the pressure, and the x-axis would be the inverse of temperature. And so the slope of the line would be negative delta H of vaporization over R, and the y-intercept would be constant C. All right, unit cells. So with a unit cell, you need to be able to look at this and determine what the formula is. It's pretty simple. So I've got these notes here if you need to memorize it, but if you can just visualize this unit cell. So if we just took one little box out of this, all right, one corner, here, let me look at this closer. So let's just picture this chlorine right here, all right. Only 1/8 of that chlorine ion is inside of that box. See that right there? That's one-eighth, right? Because you would have one piece here, one piece on the bottom and the back, one piece on the bottom and the front, another piece on the bottom and the front, and then 4 more pieces on the top, if you can visualize that. So anytime it's on a corner like that, it's going to be 1/8. And then anytime it's on the side, like down here on this one, that's going to be 1/4, right? 1/4 of that ball would be inside of that cube. If it's in the center, it would be 1 whole. If it's on the side and you can see half of it, like this right here, that one, it would be 1/2, okay? So you really only have to look at 1 cube of this on this one to see that there's 1, 2, 3, 4 in 1 cube of the sodium, and then 1, 2, 3, 4. I'm sorry, of the sodium, and then the other one is chlorine. And so what you end up getting is you end up getting NaCl. Right? So let's look at this one and see if we can find the formula for this one. All right, so for oxygen, I'm going to count my pieces. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygens, and it's on an edge, right? So it's 1/4 because of that times 12. And so that's going to be 3 for oxygen, and for rhenium, we've got 1, 2, 3, 4, 5, 6, 7, 8, and they're on a corner. So on a corner, it's only 1/8 of an atom that is actually sitting in the cube. So 1/8 times 8 is equal to 1. And so this would be ReO3 because there's 3 oxygens for every single rhenium. All right, properties of water. The boiling point is 100 degrees Celsius. The freezing point is 0 degrees Celsius. And it is polar. What type of compounds would dissolve in water? Ionic compounds. Not all of them, but most of them. And polar compounds. So nonpolar things like fats and oils do not dissolve well in water. What happens when a substance is dissolved in water? How would that affect the boiling point and freezing point, and why? So if we dissolve a substance in water, okay, so I'm going to draw my container with water in it. Okay, and then we dissolve something in here, so let's just put some salt in it. So I'm going to get chloride here and a sodium here. All right, and they're all dissolved in the water, and then we try to boil it. So I'm going to draw, let's see, an open flame. Okay. Some fire. And I try to boil it. Remember that it has to go into the vapor phase for it to boil. Well, it's not going to want to go into the vapor phase because it's comfortable sitting here with these ion-dipole interactions. Or if something else was dissolved in it, it would be comfortable with the dipole-dipole interactions. So it takes more heat to get the water to go into the vapor phase, to escape into the vapor phase. And so it increases the boiling point, and it's going to decrease the freezing point for the same reason. That's why we put salt on bridges when it freezes outside, because it makes the freezing point go down, and so it can get colder without the ice freezing outside. Okay, so freezing point depression and boiling point elevation calculations. Which of the following aqueous solutions would have the lowest freezing point? So if we look at these, remember here's your formulas. Delta T of the freezing point times I, and that's the van der Waals constant. Okay? And then we have the freezing point depression constant K times, remember this is molality, not molarity, molality. All right, and then it's the same equation for the boiling point elevation, only it's, lost my train of thought, I'm sorry. It's for the boiling point. Now, one thing you have to keep in mind, I don't necessarily write the negative sign in here, but this temperature is going to be going down, so you need to keep that in mind. If you get a change in temperature, that temperature has to be subtracted from your original temperature. And here it would be added because the boiling point is going to go up. So boiling points are high, and it makes it even higher. Freezing points are low, and it makes it even lower. That's how I remembered it. All right, so which one would have the lowest freezing point? Well, all three of these have the same concentration, so this isn't going to affect it. They're all going to have the same constant because they're all in water, they're all aqueous. So it has to be I that is making them have different temperatures. So the I for this one, because there's 3 lithiums and 1 phosphate, that means there's 4 particles for this. This one would have 2 particles, and this one would only have 1 because it's not ionic, so it doesn't separate. So I for lithium phosphate would be 4, which means the change in temperature would be the biggest for this substance. So I is only telling you how many particles it breaks up into in the solution. All right. If the normal boiling point of a solution of aspirin and chloroform was found to be 62.5, what is the molality? So boiling point says the normal boiling point of chloroform, so this is for chloroform, is 61.2, and then we have the boiling point of the solution with aspirin and chloroform is 62.5. So I'm going to take my final temperature and subtract it from my initial temperature, and that gives me a temperature change of 1.3. All right, and then I have my KB for the substance, and I'm looking for the molality. So I'm going to plug this into this equation here. 1.3 is equal to, and I is going to be 1 because aspirin isn't going to dissociate into anything. It's not ionic. And I've got 3.88 times the molality. So I'm just going to take 1.3 and divide by 3.88. And that's going to equal 0.34 molal. And so if we wanted to know at what temperature this would freeze at, we know that the molality is 0.34. Whoops. And the Kf is negative 4.90 degrees Celsius over molality. So that means that my temperature is going to go down by 1.66. So if my normal freezing point is negative 63.5, my change in temperature will be negative 1.66, and I've got an initial temperature of negative 3.5 degrees Celsius, and I want to find my final temperature. So I'm going to have to add these together. Whoa. And I get negative 1.66 times negative 63.5. Oh, minus, I'm sorry. And my final temperature would be 65.16, which makes sense. It should go down by 1.5 degrees, almost, a little more than 1.5. All right. How does the solubility of gases differ than the solubility of solids and water as temperature increases? Why does this happen? Okay, so put two solubility charts on here. And this over here is for gases. Oops. And this over here is for salts. Now these gases, if we're going to try to dissolve them into a solution, so you've got water that you're trying to put these in. Okay, they've got lots of kinetic energy, and so they're just kind of flying around up here. And if you want to get them to dissolve in water, you've got to slow them down, and the only way to slow them down is to lower the temperature and to raise the pressure. It's the only way you're going to get them to dissolve. And so at lower temperatures, they have a much higher solubility. They dissolve a lot more at lower temperatures than at higher temperatures. At higher temperatures, they're not going to dissolve very well at all. Okay, now for solids, it's the complete opposite. So these salts, sodium nitrate, calcium chloride, lead 2 nitrate, potassium nitrate, to get those to dissolve, you're going to want to heat it up because they're solids. So they need more kinetic energy so that they can move around faster, right? And dissolve in a liquid that has more energy than a solid does. So if we heat them up, they're going to be more willing to dissolve. Now there's always some kind of outlier here. This one actually dissolves better at lower temperatures. All right, that brings us to kinetics. So rate laws. All right, what is the order of the reaction with respect to each reactant? So to find the order, remember that the rate law, so we have this reaction A, 2B, and C is going to be equal to A raised to some order times B raised to some order times C raised to some order. And we want to know what each of these happens to be. So you can do this algebraically, or you can look at the different substances and try to figure out which one it is. I'm just going to do that. So for A, this one is doubling. So that's if any change happens in how fast the reaction goes, the rate, it has to be due to this change because this is staying constant here, right? And this one is staying constant. So if these aren't changing and the rate is changing, it's directly because of the change in the concentration of A. And so we're doubling the concentration of A here, and this is quadrupling because it's going from 1.8 to 7.2, and both have times 10 to the negative 2 here. So if the concentration of A is doubling, then I can write 2 raised to the m is equal to 4. And so that means that m is equal to 2. Okay, so now for the order of B, I have to look up here at these and find one where B is only changing and A and C are not. So the only one that I see is experiment 1 and 3, because here A is 0.1 and 0.1, here C is 0.05 and 0.05, but B is changing from 0.12 to 0.36. So that is going to be tripling. And if we look at this, I'm going to rewrite this 0.006 and 0.018. That is also tripling. I know that's really hard to read. 0, 1, 8. There we go. So it's also tripling. So if I triple the concentration, right, of B, and now everything else in the rate law would cancel out. And this triples, then N has to be equal to 1. Okay. Now for C, it's a little bit different. So I'm going to have to use a little bit extra on this one. Let me find a good color for this. You can see. I don't think that'll work. Black should work good. Okay, so I'm going to use this one from 1 to 2. Now with this one, we still got B changing, so we're going to have to account for that too. But A is staying constant here, so it's not going to affect the change in the rate. So I'm going to have this going up by 2, this one going up by 1.5, and this one going up by 2. So the rate is going to go up by 2. B is going to go up by 2, and it's raised to the first power, so this is for B, because its N is 1. And then C is going to go up by 1.5, and we don't know what P is. All right, so I'm going to end up having to, divide by 2 here. And so I get 1 is equal to 1.5 raised to the P. And so the only thing that could make this 1 is if P were equal to 0. Oops. So that means that it's 0 order with respect to C, because anything raised to the 0 is equal to 1. All right, so M is 2, N is 1, and P is 0. Now the overall order, we're just going to add them together. So for the overall order, we'd get 2 plus 1 plus 0 equals 3. And then to write the rate law, we'd write rate is equal to K times A squared times B. And that's it. All right, integrated rate laws. So we have the natural log of A is equal to negative KT plus the natural log of A naught. So this is A at whatever time this is. That's what that little t means. And this is initial, the initial concentration of A. Here we have the inverse of the concentration of A at some time t, and the inverse of the initial concentration of A. And then this one is just the concentration of A at times t, and then the concentration of A initially. And so if we set them all up like this, we get these linear equations. So we have y is equal to mx plus b. So y, we would have to graph the natural log of A at time t on the y-axis, like here in this graph, and t would be x. So time would go along the x-axis. This would be our y for second order, and this would be our y for 0 order. And so this is saying, what is the order of the reaction if the data to the right is found in the lab? So if these are the graphs that we get from the data in the lab, then remember these have to yield a straight line, because that is the definition of a straight line. And so this is the only one that's straight, and since the natural log of A is on the y-axis here, then that means that it has to be first order. Because when we did for second order, this 1 over A here, It didn't give us a straight line, nor did the zero order when we put it on the y-axis. So that one has to be the order of the reaction. Okay, so these problems are going to be over using the integrated rate laws for calculations. So this problem, we have butadiene C4H6 reacts with itself to form a dimer with the formula C8H12. So the reaction here is that. You don't really need that for the problem, but I thought I'd write it out. The reaction is second order. So for second order reactions, we use this. And so when I see second order, I automatically think of this. And so that tells me that this is the formula I'm going to use. Also, second order is the only one that has a positive slope. If you look here at this equation, for first order, it's the natural log of a at time t, and then it has a negative slope, kt, and then the natural log of a naught. And this one is 1 over at, so it's the same thing in the y spot, only it's the inverse of the concentration instead of the natural log. And then it has a positive k, so kt is right here, mx, and then the natural log of a naught here and 1 over a naught here. And then it's the same pattern for zero order, only it's the concentration instead of the inverse or the natural log. So these are very easy to memorize because they're all basically the same, only you have to remember for second order it's the inverse, for first order it's the natural log, and for zero order it's just the concentration. Okay, so now that we know which equation we're using, I can start to kind of piece together what I'm going to put where. And so it says the rate constant of particular temperature is 4 times 10 to the negative 2 inverse molar inverse seconds, and the initial concentration of C4H6 is 0.02. So I know that the initial concentration of A naught is 0.02, and I also know that K, this is little k, don't get it confused with equilibrium K, big K, is 4.0 times 10 to the negative 2. And the units are 1 over molar times the second. So I'm going to use this information and plug it into this equation up here. All right, and it says, what is the molar concentration? Oh, it should say of C4H6 after a reaction time of 1 hour. So our time is going to be 1 hour. So I'm going to plug all of that into this equation. I'm going to rewrite it over here. And we're looking for the molarity at after 1 hour. So I'm going to plug all of this stuff into that equation. So I've got 1 over A at time t is equal to 4 times 10 to the negative 2. Okay, now I come to a problem. I have to put time in, but if you look right here in our rate constant, it uses the time seconds, and the time that was given to me is 1 hour. So I need to convert that time into seconds so that I can properly put it in the equation so my units cancel out right. So 1 hour is 3,600 seconds. You can go 1 hour to minutes and then minutes to seconds if you feel more comfortable with that. So I have 3,600 seconds plus 1 divided by my initial concentration of 0.02. All right, so I'm going to put a box around this. All right, and that's what we're going to be solving. So I've got 1 divided by 0.02 is going to be 50. So this right here is 50, and the units are going to be 1 over molarity. And I'm going to add that to 4 times 10 to the negative 2 times 3600, which is 144. Oops. Okay, and the seconds canceled out, and so we're left with 1 over m. And that is going to be equal to 1 divided by a at time t. So now I can add these two together. They both have the same units, 1 over m. So I have 194 inverse molarity, and I want to find a at time t. So what I have to do now in order to solve for this, a lot of students stop right here and they think they have found the answer, but we haven't, because this is still 1 over a. We don't want to find 1 over a, we want to find what a is equal to, so I'm going to have to either multiply both sides by this and then divide 1 by that, or you can just look at it as you have to take the inverse of both sides, so you have to flip both of them, and so that will look like this. If I flip 1 over a, I'd get a, and then I'd get 1 divided by 194. And so that is equal to 0.00515. So that's the answer to the first question. Now I'm going to shrink it down and slide it over so I can do the next problem. All right, so the next one says, what is the time in hours when C4H6 concentration reaches a value of 0.002? So this time I have a at time t is equal to 0.002. My a naught is going to stay the same. And my k is going to be the same. It's a constant. It doesn't change. So I'm going to plug those in, and this time I'm looking for t in hours. So I've got 1 divided by 0.002 is equal to 4 times 10 to the negative 2. That's molarity. Times t plus, and remember this was 1 divided by 0.02 molar. You can barely read that. Okay, so if I try to make this a little easier to work with, I'm going to take 1 and divide it by 0.002, and so that's going to be 500. And then 4 times 10 to the negative 2 plus 50 inverse molarity. That's an M down here in case you can't read it. He's just having a little problem today. All right, so I'm going to subtract this from both sides. So it cancels out over here, and I end up with 450 is equal to 4 times 10 to the negative 2 times t. And then divide both sides. So molarity cancels out, and what I'm left with is seconds. So this becomes my time that I'm looking for is 11,250 seconds. And we wanted the time in hours. So I'm going to come over here. There's 3,600 seconds in 1 hour, and so that is 3.13 hours. So that's my answer. All right. Next, this is going to be a decay reaction, and so decay processes are always first order. It says that it's first order, so this time we'll be using this. Our first order is natural log, and it says we have a half-life of 20 minutes. And we want to know how much of the drug will remain if the shipping time is 2 hours. And we want to know, so that would be A at time t, because we're given a specific time in milligrams. And A naught, is equal to 10 grams. All right, so why are they giving us this half-life thing? They give us this to be able to find K. And so I think that it would probably be wise of you to know the half-life equation for a first-order reaction. If you can't remember it, you can always derive it. I'm going to derive it very quickly, so I'll try to do my best to write clearly. But if it's a half-life, that means that enough time has gone by to where your initial concentration is half of what it was. Or where your concentration is half of what it was initially. That's a better way of saying it. So if it's a half-life has gone by, the natural log of AT becomes A naught divided by 2. So that's half of what we started with, would be equal to K, negative K, times the half-life, plus the natural log of A naught. Now, if you remember, I can go ahead and bring this over here so that I get natural log of A naught divided by 2 minus the natural log of A naught is equal to negative K and the half-life. And so if you remember from algebra class that if you are subtracting logs, it's the same as dividing, because remember, logarithms are a function of exponents. And so if you've ever had to divide exponents, you know that you have to subtract them. So it's the same thing here. If we're subtracting them, then we're dividing them. So it's going to be the natural log of A naught divided by 2, right? Divided by A naught. So these A's cancel out. So what we end up with now is the natural log of 1/2, or 0.5, is equal to negative K, and the natural log of 0.5 happens to be negative 0.693. So I'm going to divide both sides by negative K, and my equation that I'm going to use, ends up being the half-life is equal to 0.693 divided by K. So if I were you, I would have this memorized. You can derive it like me if you want to, but this test is very long for the amount of time that you have to solve these problems. Okay, so I'm going to shrink this down so we can see what we're working with and slide it over. So now that I have this half-life equation right here, I can use this to find K. So if I do a quick rearrangement, I've got 0.693 divided by the half-life would be equal to K, and so I've got 0.693 divided by 20 minutes is equal to K, and so my K ends up being 0.03465, and it has the units inverse minutes. All right, so that is my first answer that I have to use in the next process. So I'm going to go back and use my first order reaction equation, integrated rate law, and I'm going to put in, I don't know what this is what I'm looking for, and it's going to be negative 0.0347 inverse minutes times my time of 2 hours, which we also know is 120 minutes. Since my K, I left it in minutes, so it's 120. They have to be in the same unit so that they can cancel out here. And then I'm going to add to that, slide it over just a little bit, my initial concentration, the natural log of 10. And so you can put it in grams, it'll be fine. All right, so if I take the natural log of 10, I get 2.30. So that is that. And then 0.0347 times 120 is 4.164. And don't forget to bring down the negative. And so I can add 4.164 to 2.3. And I end up getting negative 1.864. So now to undo the natural log here, I'm going to use E. And I get that my A at time t will be equal to 0.155 grams, or 155 milligrams. All right. Whoa, everything's moving around on me. So there you go. So you can see everything. All right. Okay, so energy of activation. So the energy of activation is the energy required to get a reaction to actually go. And so on these energy diagrams, it will always be this hump. So where the reactants start in energy up to the very top of the peak, here, or here in this one. So that's the energy of activation. And if you looked at a graph, it would be the one that has, reading this question, how could you tell if the reaction would be kinetically slow by looking at the energy curve? It would be the one that has the highest hump here. Regardless of where these end, it would be the one that has the highest hurdle to overcome. So let me write that down. This answer it's the biggest hill to climb, if you want to look at it that way. All right, so exothermic reaction. And exothermic means it's lost energy. And so if it loses energy, then that means the products have less energy than the reactants started with. So right here we have reactants here, and then the products gained energy. So this would be endothermic. This one, we have the products or the reactants at this energy level, and the products have much, much less energy than the reactants did. So this one would be exothermic, while this one was endo. All right, collision theory. So collision theory states that an increase in temperature causes the molecules to hit each other more often and also increases the energy at which they hit each other. So for most reactions, when you increase the temperature, the reaction rate will increase, because if they are hitting each other more often, they're going to react more often. But molecules don't only have to hit each other with enough energy to overcome the energy of activation. They have to hit each other with the correct orientation. So if we look at this picture here, okay, we have A plus BX, and we want to form B plus AX. If A hits B, then no reaction is going to happen, because we don't want A to form a bond with B. We want A to form a bond with X, so it has to hit on this side of the molecule. So here, if it hits over here, then X will be more likely to react with A and let B go, and so this would be an effective collision, while this one is not. So not only do you have to meet the energy of activation requirement, but you also have to have an effective collision. So not every collision will result in a reaction, only ones in which the orientation is correct. All right. A chemical reaction is performed at 300 Kelvin and at 600 Kelvin. The reaction has an activation energy of 50 kilojoules per mole. At 600 Kelvin, what is the ratio of K2 to K1? So very quickly, I have this equation right here, and I'm looking for this ratio. So my energy of activation is 50,000. I'm going to go ahead and convert it to joules, because R is in joules, so this needs to be in joules as well. And then 1 over 300 minus 1 over 600. All right, so if I plug that in and put that into my calculator, I get 0.001667. And then 50,000 divided by 8.314 is 6,013, 0.95. So if I multiply those two together, I get, what am I doing? Skipping ahead. I get 10.02345 and natural log of K2 over K1. So E on both sides, my ratio of K2 to K1 is equal to, I didn't calculate it. $22,500. So K2 is 22,500 times more than K1. All right, we're almost done. Identify the catalyst. So this is a mechanism, right? It's how a reaction takes place. So a catalyst is going to be a reactant on one step and a product on another step. So usually it's a reactant on the first step and a product on another step. Doesn't matter which step as long as it comes out of the reaction. So it's something that you put into the reaction and then you get it back at the end. So it's not used. Meaning it's not consumed by the reaction. Okay, so if I look at this, OH is over here on the reactant side, and then it's also over here on the product side, and so that is going to be my catalyst, hydroxide. And an intermediate is the exact opposite of a catalyst. It is formed by a step then consumed by another step. So you don't get this back out of the reaction. It's formed by a half reaction. It's formed by a mechanism step, and then it's consumed by another one. So you have no control over the concentration of this thing. It gets right here on this gets formed by this step. These are the reactants that you initially put in. This gets formed, and then it gets eaten up by a subsequent step. So this would be the intermediate. Okay, and so remember, a catalyst is a reactant first, and an intermediate is a product first. And in the overall reaction, if we add all this together, this cancels out, and this cancels out, and so we would end up with NH2NO2 goes to N2O plus H2O. So to make sure that everything is balanced, that I have the right thing, I've got 2 nitrogens, and there's 2 nitrogens. I've got 2 oxygens, and there's 2 oxygens, and then I have 2 hydrogens, so there's 2 hydrogens. All right, write the overall reaction. We're going to do the same thing here, and so I'm going to look to see if there's anything I can cancel out. HI, I can cancel that out. And that is all that I see. So if I write the overall reaction, I'm going to have H2 plus 2 ICLs, because there's 2 of them, right? And then I'd get I2 plus 2 HCl's, because there's 2 of them on the product side, so we would add them together. Okay, according to the mechanism above, what is the order with respect to each of the reactants? So the reactants here are H2 and ICl, and remember, you can write a rate law from the slow step. It's just going to be, I'm going to write it right here, rate is equal to K, and then you put your concentrations of the reactants only in the slow step, raised to their coefficients. And so since there's only one of each of these, it's just going to be to the first order here and to the first order here. And so to answer this question, it's first order for both. And so this is overall second order. It doesn't matter that this has a coefficient of 2 in it, because the second ICl is in the second step, which is the fast step. So it does not control the rate. The slowest step controls the rate. Just like if you're talking about a process that you're doing, if you're going to try to figure out how long it's going to take, the slowest part of it is going to take the biggest amount of time out of the total time. And so that's why the slow step controls the rate law. All right, that's it for part 1. Part 2 should be uploaded within the next couple of days.